We're going to continue on. We're talking chapter 2, and we're talking something out of chapter 2. I think we've been talking about measurements. Um, so remember, as we talked about, when we do take measurements, there's really, again, those two sort of things that you want to look at whenever you're using a piece of equipment. And as we talked about, there's always some degree of uncertainty associated with a measurement. And what helps you sort of understand sort of what the uncertainty will be is like looking at the markings. And again, there's usually the large markings. And as we talked about and as we saw, those usually will have a number basically associated with them. And then you'll usually have some type of small markings. And those small markings are usually the markings that are between the larger markings. And when you count those, again, you can count starting after the last large marking and ending on the next large marking. So you can figure out how many you have. However, there are many small markings you have. You could divide the large markings value by the number of small markings. And that will give you basically what each small marking basically represents. Now, what we talked about was we always want to record all the certain numbers plus that first uncertain number. And that's really what sort of significant figures are in our measurements. In most cases, you usually could go one more place to the right of the smallest markings. So if the smallest markings represents 0.1 of a centimeter, you usually could take the reading one more place to the right, which means you could go to 2 decimal places to take your reading, with the last decimal place in that case being your uncertain number. Now, that's not always the case, but I would say most of the time that is the case. So you could kind of follow that general rule of just, hey, it's, one more place to the right of the smallest marking is usually where you want to go. One way that we talked about that, if you are really confident in terms of, again, what the smallest marking represents, but maybe you're not so confident in how far you should take the reading, even before you take your measurement, all you have to do is take the small marking and divide it by 2. And that will essentially give you a number. And really, for our purposes here, the number is not that important. What is important when you look at that number that you get is however far that number goes to is how far you should take your reading to. So like the example, if our small markings represented 0.1 of a centimeter, if I divide it by 2, I end up with 0.05 centimeters. And again, what this means is on that particular piece of equipment, I should definitely be taking readings to 2 decimal places. And again, you can kind of figure that out before you even kind of take your measurement and stuff like that. Again, if you had something like 1 milliliter was your smallest marking, so you divide that by 2, you will get something like 0.5 milliliters. And that basically is 1 decimal place, which means if you have a piece of equipment that has those markings on it, you should be taking your readings to 1 decimal place. So that's just a nice way to basically figure out how far you should take the reading to before you even take the reading. As we also talked about, in some cases, that may require you to add a 0, right, to maintain the proper number of digits that you should have on the scale. Remember, we don't want to ever sort of lose significant figures, which is what our measurement really will have, a certain number of significant figures. So even if a measurement was right on an actual marking, if that piece of equipment has the ability, for example, to go to 2 decimal places, you may have to add a 0 to take it to 2 decimal places, again, to maintain the proper sort of reading that you did. That is essentially where significant figures come from. They come from measured sort of values. And we talked about really what's considered a significant figure, and pretty much any non-zero number is going to be significant. And remember that is essentially where we start counting. So we always look at a number, go left to right, and going left to right with the number, as soon as we hit the very first non-zero number, that is technically where we should be starting our sort of count on significant figures. Then we have zeros, and there's 3 different types of zeros. We have those leading zeros, which are not significant. And once again, these are really the zeros that come before you hit that very first non-zero number. So again, because we didn't hit the non-zero number yet, even if they may come, for example, after a decimal point, they are not going to be significant because of that. So again, 0.0011, none of these zeros here are significant because really we haven't started counting until we hit that very first one there, and that's where we're going to sort of get our significant figures from. There's trapped or captive zeros, and those are going to be significant. And once again, those are zeros that are essentially trapped between two non-zero numbers. So like a 404, that zero there, again, would be significant because it is trapped between two non-zero numbers. And really the one that sometimes gives, again, people maybe the hardest time is that trailing zero. And the reason, again, it gives people sometimes a hard time is because in some cases it may be significant, and in other cases it may not be significant. So again, what helps you determine whether or not it is a significant zero or zeros at the end is the presence of a decimal point. And that is going to make it significant. So once again, in this situation, when we're counting significant figures, the decimal point does need to be actually written in numbers. Again, can't just assume that it's there or anything like that. It actually has to be sort of written in a number to make those zeros at the end significant. Again, if you do not have an actual decimal point written in the number, then those zeros at the end would not be significant. Now, these again are sort of the rules we follow for significant figures. There are other types of numbers that we also touched upon, which are considered exact numbers. And exact numbers are, again, things that we either count or basically is like a definition or an equality. And again, the classic example of like apples in a barrel, you're just going to count how many apples you have. So that would be sort of an exact number. Another more common way that we come across exact numbers is a definition like, again, 12 inches is 1 foot. So that is considered an exact number. The deal with exact numbers is truly they can have as many significant figures as you want. So sort of the good news, as we'll talk about a little bit more here today as well, I think. The good news is if you do come across an exact number in a calculation, you don't have to worry about it in terms of your answer and like how many significant figures you should give your answer to. We basically kind of ignore those. And that's because, again, they could have sort of an unlimited number of significant figures. So because everybody could kind of pick whatever number they want, we sort of ignore those sort of guys. Now, we also talked about scientific notation again and significant figures. And again, as we talked about, all the numbers before the times 10 part, when a number is written in scientific notation, is going to be significant. So again, as we also talked about, one of the benefits of scientific notation is just that you could really kind of control how many significant figures you need in that number. And it is, again, in certain cases, the only way to give the answer to the correct number of sig figs sometimes is to write it in scientific notation. So, and again, because you could kind of control how many you have, how you write it, that's sort of what we got going on there. I think we finished up on talking about calculations with sig figs. And again, as we talked about, there's really kind of two groupings of math that we do. We can multiply or divide. And when we do multiply or divide, it is significant figures we're looking at, and it is the least number of significant figures. So if you're multiplying or dividing a bunch of numbers together, the one that is the least number of significant figures is how many significant figures your answer should have. And that's a little bit different than what we do when we're dealing with adding or subtracting. So again, when we're dealing with adding or subtracting, it is decimal places that we're looking at. Again, not significant figures. And it also is the least number of decimal places as well. So again, the numbers you're adding or subtracting, the one that has the smallest number of decimal places is actually how many decimal places your answer should go to. Once again, not how many significant figures, but how many decimal places that your answer should go to. The idea behind that is, as we also talked about, essentially your calculation that you're doing is really only as good as your kind of worst measurement. And those would have, in most cases, the least number of significant figures or the least number of decimal places. And that's really what limits how good your calculation is sort of that kind of least best measurement that you made. We also talked about a couple other important things, right? In terms of rounding, right? We don't want to go crazy on the rounding, right? We want to round to the proper number of significant figures. We also want to kind of avoid rounding, right, till we are towards the end of the problem. We do want to kind of keep track of everything along the way, but we do want to kind of clean everything up at the end. You definitely want to keep a few extra digits if you are getting answers in between and continue to use those numbers. That will help with some rounding errors and stuff like that. Just take a few extra digits and stuff like that. Any questions on any of that stuff there? All right. All right, so just looking at a couple of these here, we got 6.25 times 1.5. I could read, I think. Let's see. That gives us on the calculator there 9.378. Reminder, obviously, your calculator doesn't give you things in the proper sig figs. So here we are multiplying, right? So we should be looking at sig figs or decimal places. Sig figs, right? So first number's got 3. This number's got 2. So once again here, our answer should go to 2 significant figures. That would take us to the 3. We again would want to look at the number next to it, which is a 7. So that is above 5. So we're going to round up. So a 9 point, dramatic pause there, 9.4 there would be a good answer there. And again, that gives us our 2 significant figures. Here we're dividing. So once again, when we're dividing, we're also going to be looking right at significant figures. So if we take a look at our first one here, that's got 4 significant figures. That's got 3. So again, it is always the smallest or the least when you're doing this. So we're going to go 3. Which number would be my third significant figure when I look at that answer? Which was my third significant figure? It is the 8, right? So again, leading zeros, not counting until we hit the 7, right? And the 5 and the 8 here would be our third significant figure. In this case here, that's less than 5, so we're going to actually drop it in this case. And we would end up with 0.0758. Why do I drop these numbers and not put zeros? If I put the zeros, I would have a lot of significant figures, right? Way more than I need, right? So again, remember, in certain cases, you do need to drop zeros. In some cases, you may need to add zeros, right? But in this case, we would not want to put those zeros at the end because they would be trailing zeros, and this number has a decimal point, and then they would then become significant, right? Here we are adding. So in this case, we are not looking at significant figures, but we're looking at decimal places. So we got 2 decimal places there. Looks like 1 there, and looks like 3 there. So 1 looks like a winner, and that would take us here. Again, we would take a look over here, and that is less than 5. So we're going to go with 29.1. Looks like a winner. This again has 1 decimal place, but a reminder that, again, it also has how many significant figures? Does have 3, so that might be important if we are continuing on and using that in another calculation, right? So we want to keep that in mind. And lastly, here we're subtracting. So once again, we're looking at decimal places. So we got 4 there, we got 1 there. So that is going to be 1 decimal place here we want to go to. Looking at the number next to it, which is an 8. So we're going to round up in this case. So it's 0.6 in this case, yeah. Any questions on any of those? So we might have talked about last time if I took 12 plus 1.11 plus 3.2 and I add that together. So 1, a 3, 3, 5, 6, and a 1 there. What should my answer be on this one? Yeah, so in this case, we are adding, so we're looking at decimal places, right? And this one has no decimal places, so that is the smallest number of decimal places. That is 2, that is 1. So in this case, we would go to a whole number in this case, yeah? Any questions on there? All right. Now, I think we touched a little bit upon this earlier, but again, we do use prefixes a lot, and they do come up. And we do want to make sure we do kind of use the prefixes correctly. And For example, kilo is 1,000. You will also sometimes see it on the table kind of listed as 10 to the 3. And again, when you do see kilo listed as 10 to the 3, once again here, this is scientific notation. This is basically 1 times 10 to the 3. So if you needed to, for example, punch that in your calculator, you would punch it in like we talked about in terms of scientific notation. Now, once again, I might mention this earlier when we saw it, but just officially here, again, it's very common people sort of use this kind of conversion backwards or incorrectly. So when you do see this sort of number here, that again is how much there is in the base unit to one of the prefix units. So if we're comparing, for example, something like we have there, kilometers and meters. Now, kilometers is our prefix unit. This is our base unit. And our base unit here is the same unit in each. And this would mean in one prefix unit, there would be 10 to the 3 meters. By the way, 1 times 10 to the 3 is 1,000, which is why 1 kilometer is 1,000 meters, right? So it's the same, basically, conversion there. And again, it's a very common thing. Like I said, maybe earlier, people will sometimes always kind of want to do that backwards and do like 10 to the 3 kilometers is a meter. So that is, excuse me, the proper way to use that. Again, it doesn't matter really what the base unit is, as you can kind of see there with their examples. But again, if you went like that to kiloliters and liters, it would work the same way. This is our prefix unit. So 1 kiloliter would be 10 to the 3 liters. So it doesn't really matter kind of what the unit is, if you will. It's always one of the prefix units to whatever that number is of the base unit. Here is a table kind of from your book there of some of these common sort of prefixes. I'll be honest with you, I don't know how much tera, giga, and mega will come across. Maybe a little bit, but definitely kilo you do see a lot, which again was that 10 to the 3. And definitely deci, centi, milli does pop up a lot. You know, those kind of conversions there. Again, centi being 10 to the minus 2. Once again, if we were doing something like centimeters and meters, centimeters is the prefix unit, meters is the non-prefix unit, and that would mean in 1 centimeter there is 10 to the minus 2, or 1 times 10 to the minus 2 meters associated with it. Now again, you can use maybe the bigger number version of this. If you take 10 to the minus 2 and divide it to both sides, this becomes 1 meter is 100 centimeters. So that is really the same conversion. It's just dividing it out the other way. So you sometimes will see it in that vein as well. Now, again, doesn't matter if it's different units. So 1 centigram would be 10 to the minus 2 grams. And again, we always want to kind of use these correctly. I would say maybe on the exam, they probably will be given to you in this sort of form, like, you know, centi is 10 to the minus 2 or kilo is 10 to the 3. So you want to make sure that you know how to kind of use those correctly. So for example, if we were doing an actual conversion, and we'll kind of touch upon what's coming up here, but if we were doing a conversion, and let's just say we had 626, we'll do centigrams, and we want to know how many grams that is. So we do want to kind of, again, set these things up correctly. So first off, to sort of touch upon some of the stuff coming up here, what we see is we want to look for what is known as an equality. And an equality is, again, basically a definition, like 12 inches equals 1 foot. It's basically two values that are in different units, but represent the same amount of something. So same idea, if you had 100 pennies, that is the same amount of money if you had $1, right? They represent the same amount of money. They're just sort of different units. So again, we could go to that table, and as we just talked about there, we could see centi is 10 to the minus 2. And that would get us our equality of, again, 1 centigram, actually, is going to equal 10 to the minus 2 grams. And again, that is the proper way to use that. That right there is basically what is known as an equality. And one of the things that we do with equalities is this: we can basically write conversion factors that allows us to basically solve for things. So we could get a conversion factor from this equality. And a conversion factor really is nothing more than just a fraction. And basically just make a fraction with those two values. So one conversion factor is you could put 1 centigram up on top and 10 to the minus 2 grams on the bottom. Or you could make another fraction, which is just the opposite of that. You could go 10 to the minus 2 grams up on top and 1 centigram on the bottom. And this will get you basically your conversion factors. And that is pretty much the deal for any type of equality. You essentially could get two conversion factors from any equality that you have. Will you use both of them in a problem? The answer is no, you will not, because you will undo your calculation if you use them both. You will just use the one that you actually need. Now, the reason we kind of write them in fraction form is the way that we sort of show work, and you're sort of expected to show work in chemistry, is through a process that's known as dimensional analysis. And that's a fancy word to basically say, I guess two fancy words to basically say, we're just going to use a conversion factor to get rid of units we don't want and end up with units that we do want. So when we set up problems and we use conversion factors, what we want to use is dimensional analysis to do that. And when we use dimensional analysis, there's pretty much three things you have to remember. And we're going to talk a little bit more about this a little bit later, but jumping the gun a little bit. So basically the three things you have to remember to always make this work out good for you is, first thing is very simple: opposites cancel. So if you have units up on top and you want to get rid of them, you got to put the exact same units in the opposite location on the bottom. Or if you have units on the bottom you want to get rid of, you got to put the same unit up on top. Basically, opposites will cancel each other out. The other two is pretty straightforward. It takes care of the math part of this, which is anything on top gets multiplied. And the third thing is anything on the bottom gets divided. And that's pretty much it in terms of dimensional analysis, in terms of what you need to do. So you want to think about these things and set these things up in a way that it's very much like a fraction. There's a top, there's a bottom, and you want to put units on top and bottom. So the idea here is, for example, I'm going to take my number I'm starting with, and I'm going to start with that 626. Technically speaking, the number I'm starting with is not a fraction, right? But technically speaking, you could make it a fraction simply, if it helps you, by just putting it over 1. And when I do that, I could clearly see my centigrams are on top or bottom. They're on top. And if I want to get rid of centigrams, I need to put them then in the opposite location, which means it needs to go on the bottom. That makes our decision for my conversion factor hopefully very simple. Which conversion factor has centigrams on the bottom, the one on the left or the one on the right? The one on the right, yeah. So I'm halfway done with the problem here, and all I had to remember is opposites, right? So that is what we're going to use. And we're going to make sure that we do set it up still in like fraction form here. We're going to put 10 to the minus 2 grams on top and my opposite location there with my centigrams in this case. Now, at this point, what's going to happen is math is always in this situation. Anything on top gets multiplied. Anything on the bottom gets divided. Yeah, so that's pretty much it. So what happens when we do the math part of it here is the centigrams on top and bottom will actually cancel out. So it's really the same thing as if I asked you, if I took 2 divided by 2, what does that equal? Equals 1, right? And if I take 4 divided by 4, it equals 1. So if I have centigrams on top and centigrams on the bottom, it equals 1, and they cancel out. Yeah, so it's the same idea. And that is how those units basically cancel out. Where basically you have the same units on top and bottom, they divide themselves out, and they essentially will cancel one another. That also leaves me, when I look at my setup here, only one unit left, right? The only unit that's left that did not cancel is grams here, right? And it's on top. And that typically is what you want if you're solving for something with one unit. You want it to be up on top by itself, no other unit there. It is possible you might need two units, one on top and bottom, but if you're just solving for one thing. So really all we have left here to do is the math part, which is I'm going to take 626 there, and I'm going to not make it negative. I'm going to take 626 and multiply it by 10 to the minus 2. And once again, that is 1 times 10 to the minus 2. So you would punch that into your calculator like you would do your exponent type number like normal. And if you do that there, we will end with 6.26 here along the way. And our units here would be grams. Now, when we give our answer here, the other really nice thing about dimensional analysis and setting these problems up like this is the absolute only calculations you do is multiplying and dividing, which means when I'm thinking about my answer at the end, what thing should I be looking at? Sig figs or decimal places? I should be looking at significant figures, right? Because when I multiply and divide, my answer should have the same number of significant figures as the one with the least. By the way, this is a metric to metric conversion, which means that's an exact number, which means we don't even have to worry about that number, which means the absolute only number here that has significant figures is our very first number, which is 3 significant figures. And that means my answer should have 3 significant figures as well. So again, if you come across something like we were just talking about with exact numbers in a calculation, you don't have to worry about them. You just have to worry about any numbers that are not exact for your answer. Yeah. So again, it kind of depends on your calculator, but if I was punching this in, let me go, I'll go here. So six. So if you were punching this into your calculator, you would go 626. You would then want to actually hit your multiplication button because you're multiplying that number. And basically the next number is 1 times 10 to the minus 2. So you could punch that in and hit the 1. And then you want to hit your exponent button. And then you want to hit your negative button and 2. And then hit equals. And yeah. 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 So again, you want to make sure again. So basically, that's in scientific notation. So you definitely want to make sure, as we talked about with scientific notation, that you're using exponent button. Honestly, on some calculators, for example, like mine, you don't even have to put the 1. You can just hit the exponent button, -2, and it'll work out okay. But if you want to be safe, just punch that number in. And it's always when you see like 10 to the 3, 10 to the minus 2 in that table, it's always 1 times it, and that's basically 1 times whatever that exponent is, and that's how you would punch it into your calculator. Yeah. Other questions? So this is basically dimensional analysis, and as we'll talk about here, officially dimensional analysis is coming up, but this is a really good way to do your calculations, and you should do your calculations this way. Some of the benefits that we'll talk about is if you take a dimensional analysis approach to some problems, it may not even require you to remember a formula. It may not even require you to rearrange a formula. All you have to figure out is what units I need to get rid of and which ones I need to end up with. And if you set it up in this sort of dimensional analysis way, because it's built in with you always multiply the top and you always divide the bottom, that builds in the rearranging of some formulas, and you don't have to worry about that, and it will kind of take care of itself. And sometimes it's a really helpful sort of way to do things as we get into other chapters as well that have formulas when you do have those type of situations. Questions on that? Now, for example, from a prefix to another prefix. well, all that kind of stuff, right? So, a really good way if you're kind of going from like a prefix to a prefix. So let's just say we had we'll go 63, 30. We'll go centimeters to kilometers. Yeah. So let's just say we're just going to start with centimeters and we want to end up in kilometers. So this is basically X, right? The base unit here is meters for both of them. So my recommendation is you will probably have like that table given to you. And because of that, it's probably the best approach here. You take it easily on that table, find that conversion. Base unit to the next prefix unit. And that's probably the best way to do it. And you'll probably get the right answer. So if we took that approach here, once again, we would be using centi, which is our 10 to the minus 2. We also have kilo here. And again, if you go to that table, it is 10 to the 3. And again, that's basically 1 times 10 to the minus 2 and 1 times 10 to the 3. Again, our qualities that we would have for our centi is very similar to what we had on the previous one. 1 centimeter, which is our prefix unit, will be 10 to the minus 2 meters. And for kilo, 1 kilometer, which is our prefix unit, 10 to the 3. These are our equalities. And just like we did on the left, can get 2 conversion factors for each of those. So we can have 1 centimeter over 10 to the minus 2 meters, or 10 to the minus 2 centimeter. So can have 2 conversion factors. We could have 1 kilometer. Again, these are sort of our conversion factors options. And again, once you kind of figure out a pathway and once you kind of got your possible conversion factor, again, one dimensional analysis. So just like before, I'm going to start with my number that was given. And I know I want to get rid of centimeters. So I, you could just put it over 1 so you can visually see it's on top. Not necessarily have to do that, but if you want, you can. And once again, now just got to remember, right? So I want to get rid of my centimeters. So when I come up to my first options of conversion factors here, I am going to want my centimeters in the opposite location, which in this case is the one here on the right, should be that. So we want to also make sure that when we set this up and we write it, we keep this sort of fraction thing, top and bottom thing going. Some people call it like railroad ties and stuff like that. We're going to go 1 centimeter on the bottom and 10 to the minus 2 meters here on top. If I stop the calculation right at this point, what units am I in? I am in meters, right? Because again, we're going to multiply here. We're going to divide here. When we divide, the centimeters on top and the centimeters on the bottom will basically go away. And that leaves us just meters on top. At this point, you really do have 2 options. You can, if you wanted to, you could get an answer at this point and then continue on with the next conversion. Or since you already got it set up and you know that's not where you need to stop, you could just continue on with the calculation. And again, because I wrote it the way I wrote it, it's very clear that my meters are up on top, right? Which means to get rid of my meters, they need to go on the bottom, right? So the opposite location. So when I go to my conversion factors for meters and kilometers, which one should I choose, the left or the right? I should choose the one on the left, right? Again, that has the meters in the opposite location. I want to get rid of these meters, which is on top. So to do that, we go opposite. We're going to go 10 to the 3 meters is 1 kilometer. We are still, I built onto this, still multiplying whatever's on top, doesn't change. And I'm still dividing whatever's on the bottom, doesn't change. So again, everything on top gets, everybody on the bottom gets divided. Once again, when we divide, meters go away, meters go away. And I have successfully done that, right? I am left with kilometers, which is what I'm looking for. By the way, if you set it up like this and you don't end up with kilometers on top, you messed up somewhere, yeah? So again, setting it up like this will allow you to see that maybe you messed up if you don't end up with the right units other on top. All right, so now I need to do the math. We're going to multiply the top. And again here, once we're done multiplying the top, you can really multiply as many numbers as you want up on top. Once again, you probably want to hit equals once you're done multiplying. And then you want to divide by what's on the bottom. And in this case, there happens to be only one thing to divide by the bottom, but if there's multiple things, you want to divide the first thing by the bottom, hit equals, divide by the next one, hit equals. And kind of keep hitting equals and dividing, you get the right answer. So I'm going to take, again, 6335, we're going to times it by basically 1 times 10 to the minus 2. Again, we want to use our exponent button when we do that. We're going to hit equals because that's pretty much all we have to multiply up on top. Everything else is a 1. We're going to divide by what's on the bottom. We really don't have to divide by the first. The only thing we have on the bottom is 10 to the 3, which is again 1 times 10 to the 3 in scientific notation. Three. Let's try that again there. All right, and on your calculator, hopefully you went. Okay, so yeah. So again, if you were going to punch this in, here's what I would do. I would go 6335. Once again, hit the multiplication button, and we go 1 exponent button, negative button, and 2, and that basically will take care of all the top part. Then again, it's basically this number here, which is 1 exponent button, and then hit equals, and you should hopefully end up with that. Yeah. What question? Okay. So as we'll talk about efficient a few slides down the road here, kind of jumped the gun, but this is um, it is much better to do it this way because again, it really does take care of a lot of the math part of it. It also takes care of slowing out quickly. Sometimes when people don't set up problems like this and they just kind of, you know, 6 miles per hour divided by 32 feet per second. They're not sure at this point, should I be multiplying, dividing? So if you just keep it really clean and just sort of fraction way there, top, bottom, you'll always know what you should be doing because again, always on top, multiply, always on the bottom, divide. You don't have to really think about, what I should be doing. And I can tell you, as we'll talk about, there's a lot of times when people will be multiplying things when they actually should be dividing. And again, it's because they don't really keep it sort of separated like that. And they're just like, well, I think maybe I multiply or divide here. That might work. I got a 50-50 shot at it. Any questions on prefixes? Yeah. You will have probably not that exact table, but you'll have a table similar to that where it would probably say something like centi is 10 to the minus 2 or kilo is 10 to be able to make sure you know how to use it properly. Other questions? Okay. All right. So some of these equalities, again, they do represent the same amount. And these, I would say, are some common sort of length equalities that we do kind of see a lot. 1 meter is 100 centimeters. And again, that is the sort of opposite of 10 to the minus 2 meters is 1 centimeters. So again, by dividing out, you can kind of get the larger number. And that's also our milli sort of conversion. Milli is basically 1,000. Millimeters is 1 meter, but milli is 10 to the minus 3. So this is 3 meters is 1 millimeter, and this is the same as what we saw there. 10 to the minus 2 meters is 1 centimeter. So again, these are really the same sort of qualities. Just we divided everything to the other side and got kind of the larger number to use. Volume. about earlier, that's definitely the one. Just probably one you should remember because you'll use it a lot. Even if you don't want to remember it, you probably will eventually remember it because you probably use it a lot in calculations and stuff like that. And again, the other sort of one, right, our cubic centimeter is 1 milliliter, right? So that also is, just a conversion that does pop up a lot. I think that's what's maybe on the next slide right there. And we also talked about CC, which is also an abbreviation for a cubic centimeter. Again, a reminder that if we kind of take a length measure and we cube it, a lot of times that is a volume rather than a length type of value. All right, I think we talked about that. And I would say definitely probably these sort of mass conversions are also ones that we do see a lot. 1,000 grams is a kilogram, and 1,000 milligrams is a gram. And again, those are just the larger number of the kilo, again, and milli sort of conversion off of that list. All right. I think we're going to come here. So we sort of just touched upon it, but let's officially talk about conversion factors and dimensional analysis. So as we saw there with our prefixes, conversion factors really are just fractions, and you will always be able to get two conversion factors from any equality that you come across. And as you saw in some of those examples we just did, you definitely will not use them both. You'll use whichever one that you need. And again, the idea is you're just gonna put one up on top and one on the bottom, and then just kind of flip it around to get the other conversion factor. So just like if we had, again, our 12 inches equals 1 foot, we could write two conversion factors: 12 inches over 1 foot, or 1 foot over 12 inches. And again, those are sort of available to use in a problem. Now, that was our penny example that we talked about. That's a lot of words just to get that penny out there. Let's talk a little bit about some common equalities. And as we talked about with units, there's again the US units are the English units, and there's also the metric units as well. And in this column here, these are some common kind of US to US conversions. These are metric to metric conversions. So earlier we were talking about sort of what's considered an exact number. Definitely, if you're using any US to US conversion, it's going to be considered an exact number, which again means you don't really have to worry about it in your calculation in terms of your answer. If you're using any metric to metric, basically anybody in this column or any other metric to metric, it also will be considered an exact number. So once again, you don't really have to worry about that conversion factor in your calculation in terms of what your answer should end up being. The column over here is metric to US, and out of all three of these here, this is the only column where you do have to, if you go over from a metric to English conversion, or at the significant figures in that conversion factor when you're doing a calculation. There are a couple of exceptions. This guy here is probably the main one. This is considered an exact conversion. So even though it is kind of crossing over metric to English, 1 inch is exactly 2.54 centimeters. So that's considered an exact. But really anything else that you would maybe pull, for example, from this column, if you use it as a conversion factor, you would have to take into account its significant figures. So for example, if we took a look at this guy here, that is the equality, which would give us two conversion factors: 946 milliliters over 1 quart. Our 1 quart up on top is 946 milliliters. So again, these are the two conversion factors that you get from this. So if you were to use either one of those in a calculation, and at the end when you're kind of looking through everything and going, do I need to think about, the sig figs here or here? You do have to take a look at the significant figures here. Now, a lot of times when you have a conversion factor like this, one of the numbers, I say this without saying it twice, but one of the numbers will be 1. Yeah, will be the number 1. So this 1 here is not the number we would look at because it will always kind of be 1. So we would actually look at the other number, and this would count as three significant figures. So if we were using that in a calculation, we would have to kind of count that as three significant figures and take that into account and see if that is the lowest number of significant figures. I will say not in all cases, but in a lot of cases, it's still usually like the first one is usually pretty close to the right number of sig figs, the first number that you use. So again, that is the only time that you have to kind of worry about a conversion factor is if you kind of cross over metric to US. The other time that you may have to sort of worry about a conversion factor is if it's really not a conversion factor that is like a standard conversion, like 12 inches is a foot, right? It's always 12 inches is a foot. But it is like specific for the problem and you're given it in the problem. Like, for example, you come across a problem that says, hey, you're driving 55 miles per hour, right? Everybody doesn't always drive 55 miles per hour, right? That's specific for that particular problem that you're doing. That would be a conversion factor if you used it in the problem that you would need to look at the significant figures. So if you're sort of given some information in the actual problem that's kind of specific for the problem, and you can use it as a conversion factor, you typically also need to kind of take that into consideration in terms of the significant figures. Any questions on that? You will be provided with these some conversions. So again, just need to be able to use them. So let's just talk about, again, writing conversion factors here. So that's my equality there, my 5,280 feet in a mile, which, by the way, also comes up a lot in chemistry, 5,280 feet in a mile. That's going to give us two conversion factors. And once again, we're just going to simply write two fractions. So I could start with 5,280 feet on top, and that is basically 1 mile on the bottom. Or I could flip it around and put the 1 mile up on top and the 5,280 feet on the bottom. And again, always could get two conversion factors from any equality. Again, in this situation, they both represent the same amount of distance or length in this case. Again, they're just on different units. Question on that one there. Speaking of driving so many miles per hour, if I'm driving 65 miles per hour, whenever you have some type of value that is something per something, that's basically a fraction. Yeah. So basically what that means is, in case you didn't know, if you're driving exactly 65 miles per hour, that means you could go 65 miles in 1 hour is basically what that means. Good luck around here, but maybe do like 2 miles per hour when we get there more. Or we could flip this around and go 1 hour is 65 miles. Here you could go. And again, always sort of fraction. In a situation like this where you have a lot of times something per something, the number usually stays with the first unit, and it's usually 1 of the second unit. So here, hours is kind of the second unit there, and that's usually 1. And the number kind of stays with the first unit here, which is miles, and that's usually how we sort of do that. If I filled up my gas tank with 91 octane and it costs $3.05 per gallon. I'm laughing because that was expensive when I wrote it, just so you know. Now I'll be like, I'll just fill up everybody's car with that. I think that's a great deal. So basically what that means, obviously, as you maybe know, if you've gone to the pump recently, you probably won't see this number, but you can pay $3.05 and you get yourself a whole gallon of gas. Or 1 gallon of gas will cost you $3.05. And as we've been talking about, obviously, we would choose whichever one we want in terms of dimensional analysis, where opposites will, again, cancel out those units if we were doing some type of problem. Another really common thing that comes across a lot of times in chemistry is percentages. So sometimes in a problem, you're given like a percentage of something. And as you may know, one of the best ways to maybe turn a percentage into like a usable sort of number or conversion factor is to assume you have 100 of it. Like if you got a 90 on your exam, you probably got 90 points out of 100, right? So it's just easier to keep it. It keeps the numbers the same. So for example, if we had 12% body fat by mass, that would mean perhaps you have 12 kilograms. You want to go kilograms there of body fat in 100 kilograms of body mass. And that would give you two conversion factors, 12 kilograms of body fat over 100 kilograms of body mass. Or again, you can flip it around and do 100 kilograms of body mass over 12 kilograms of body fat here. Or you could even, for example, right, go the English sort of units, right? 12 pounds of body fat would equal 100 pounds of body mass. And again, that would give you your two similar conversion factors, 12 pounds body fat over 100 pounds of body mass. And you could flip it around as well. 100 pounds body mass. We'll go up top. 12 pounds body fat. Just in general, if you're given a percent of something, and we sometimes see this a lot with solutions and concentrations. So as we'll see in a later chapter, you could have something like 4.5% by mass, like sodium chloride solution. And the M/M here is basically mass to mass. So something like grams. So if you want to convert like something like this into like a usable conversion factor, you could assume 100. And that would mean in this case, you would have like 4.5 grams of sodium chloride in 100 grams of solution. Or in 100 grams of solution, it should contain about 4.5 grams of sodium chloride. So again, that's a very common sort of thing that we'll see in a later chapter. And a lot of times you are given things in percentages. And as I was saying earlier, when you have something like that, for example, with the percent mass to mass, there's usually a formula that goes along with it. And if you are given the percentage, you can turn it into a conversion factor. And as I was talking about before, take a dimensional analysis approach to that problem, and you wouldn't even have to worry about the formula or rearranging the formula. Just get rid of the units you don't need, keep the units you do need. And again, it will just kind of do it for you. And again, that's usually very, very helpful rather than having to maybe remember the formula or trying to figure out, did I rearrange it right? Or, did I move things around correctly and stuff like that? Any questions on that there? All right, so dimensional analysis, as we sort of saw in those examples, again, is a process where we kind of cancel out units we don't want and keep units we do want. So if we had a certain unit of A and we wanted to get rid of it, once again, we would put that exact same unit in the opposite location. We would put the unit that we want perhaps up on top. And as I mentioned before, those are really the three things you got to remember. Opposites cancel. Up on top, we multiply. On the bottom, we divide. And that's pretty much it. You just want to kind of set everybody up top, bottom, and remember those things. And you should get the right answer along the way, as long as you choose the right conversion factors, obviously. And it should lead you to the right answer. Now, there's several steps that we typically do follow when we're doing dimensional analysis. And you might not have to do all these steps, but if it does help you, you may want to go through all these steps. Sometimes it's really good to write what's given to you in the problem, maybe label what it is. That's a really good sort of approach. Also, in case you are given some type of conversion factor in the problem, you kind of pull it out and kind of look at it and see, oh, I think I could use that as like a conversion factor or something like that. You want to write what you're looking to find. That's always a good thing to know. Like, what am I trying to find in this problem? Not just get halfway through and go, what was I solving for again? That might not be a good thing. You want to find like a good pathway to get you to what you're trying to end up with, right? So you basically have some units you want to get rid of. You got some units you need to end up with. You want to find, in a lot of cases, maybe the shortest pathway to get there, or just any pathway to get there. And in just typical conversion type problems like this, there can be multiple ways to get to the same answer. So depending on sort of what qualities you choose or what conversion factors you choose, there may be actually different ways to get to the same end result. And it's not one's not right and one's not wrong. Just maybe it chose a sort of a different pathway. Once you have your equalities, you want to think about what conversion factors you have available to you, and then you want to set up the problem. That's really the most important thing here is, again, setting up that problem, top and bottom fraction type approach all the way across. And you should probably solve the problem with the proper number of significant figures and all that good stuff when it's all said and done. So obviously here, this is a pretty straightforward one. We want to know how many pennies there are in $3. So we have dollars and we want to end up at pennies. So obviously, probably, hopefully know that conversion. 100 pennies is equal to $1. That again is our equality. And that's going to give us our two conversion factors to use here. 100 pennies over $1 are $1 over 100 pennies. That's going to be our conversion factors. And now we're ready to really set up our problem. So as we kind of been talking about, you could start with usually the number given to you. And sometimes people do struggle with that, like what number should I start with? So usually I would say you should start with the number that's given to you. And it's usually, I would say, maybe the number that has just one unit. It's usually a good one to start with. If you have like two numbers given to you and one is like 1 unit and one's like something with 2 units, that 2-unit guy is probably a conversion factor you're going to use. And the guy with the 1 unit is probably the thing that you maybe want to start with. Once again, if it helps you just to visualize it, and again, you don't have to do this, but if it helps you, just throw it over 1. And again, now you got set up here your top and bottom, which then you just roll to opposites, right? So we obviously want to get rid of dollars, which is on top. And that means that when we go to our conversion factor, we do want to find dollars in the opposite location. And that's what we're going to use here on the left. We're going to put it there on the bottom and 100 pennies up on top. And now we pretty much have everything we need. Again, we always know the math part of it, always multiplying the top, always dividing the bottom, always 100% of the time. If you set it up like this, this is what you should be doing in terms of the math part of it. And when we do divide that, that is again where our dollars are basically going to cancel out. So we're basically just going to take 3 times 100 in this case, and that's going to give us 300 pennies. And we do want to think about, significant figures. And once again, I say significant figures because if you're doing dimensional analysis, as I mentioned earlier, you are only multiplying or dividing. So it's always about significant figures when it's all said and done. And once again, this is definitely an exact conversion, so we don't even have to worry about it. So really, once again here, the only number we got to kind of look at is this one, which looks like it has 1. So I would say that's probably good with 1 significant figure there. That is also perhaps why I did not put a decimal point at the end, because if I did, I would have how many significant figures? I would have 3 significant figures, right? So again, we want to be careful not to fancy up our answers, right, with some decimal points or something like that, because you could actually be changing the number of significant figures that you have. Okay, we're going to continue on here. So let's take a look at some more examples. There we go. So why don't you give this one a go? You're at the local AM/PM. You decide to get the 32 fluid ounce drink there. Diet Coke from the Thirst Oasis. Clearly, you go with crushed ice because nobody goes cubed, right? Everybody goes crushed ice, right? How many gallons of Diet Coke did you drink? Here's some equalities that might be helpful. 1 quart, 32 fluid ounces, and 4 quarts is a gallon. So take some moments here, set it up with dimensional analysis, and see what you end up with. Okay, so let's take a look, see how you're doing. So once again, here we have a problem. So a really important thing to do, just in any problem that you come across, is just pull out the information. So obviously, we are given in this case here, we got 32 fluid ounces. We are looking for, in this case, how many gallons, right? So what we want to do after we do that, right, is just try to find a pathway that will get us there. And like I said, there could be different ways you could get there. Since I gave you these equalities, probably the pathway hopefully you chose. So one way we could do that, obviously, is we could take the fluid ounces to quarts. And once we have it in quarts, we again could take it from quarts down to gallons. So sort of that sort of pathway. So since we have each of these equalities here, we could write our conversion factors that we could use in this problem. We could write for the first one, 1 quart is 32 fluid ounces. Our 32 fluid ounces is 1 quart. For our other one here, we have 4 quarts is 1 gallon as a possible conversion factor, or just flipping it around, 1 gallon over 4 quarts. So again, these are really our conversion factors that we could use in this problem. So now that we have that, we usually always want to kind of start with what's given to us. So we'll start with that. And again, we're going to set it up with dimensional analysis and make sure we do kind of do the fraction move. So again, if you want to just pop a 1 underneath that number there, since there's no real bottom unit or anything like that, you can. This again makes hopefully the decision making a lot easier for you. We know we got to get rid of fluid ounces and it's on top, so we need to put it on the bottom, right, to get rid of it. And that should be our conversion factor here on the left to start with. Again, also almost just as important when we do the calculation, we want to again maintain that top and bottom with our conversion factor as well. So we got 1 quart up on top and 32 fluid ounces on the bottom. If I stopped right at this point, what units I'm in? I'm in quarts, right? Because again, math-wise, I know I'm multiplying and dividing the bottom. So that dividing of the bottom is going to get rid of those units, and we're left with quarts. We're halfway home there. We have quarts now. Clearly, we can see up on top, and we now want to get rid of quarts. So once again, opposites to get rid of. So I look at my options for conversion factors, and hopefully we see right on the right-hand side here, we have our quarts in the opposite location. So again, just building off of what we were doing here, we're going to put our 4 quarts on the bottom, our 1 gallon up on top. Again, even though we're building out here, math is still the same. We're still multiplying the top and dividing the bottom. Doesn't matter how many of those you put together, it's always just going to multiply the top and divide the bottom. So again, the math is sort of taken care of for you. By dividing that bottom there, that is going to get rid of our quarts. We know hopefully we did this correctly because we now have the unit we're looking for up on top by itself, and that is definitely where we want it to be. All that's left is the multiplying and dividing part, right? So we're going to take 32 divided by 32 and hit equals, and we're going to divide it by 4, and we're going to end up with 0.25 gallons in this case. We want to also think about significant figures. Once again, we really don't need to look at this guy, exact conversion, exact conversion. So once again here, like in most cases or a lot of cases, we kind of default back to that original number, which is 32. That is 2 significant figures, which means my answer should have 2 significant figures, which it does. By the way, this is the answer, 0.25. 1 divided by 4 just makes me think you're too lazy to divide. Yes? So that is not the right answer. Never leave your answer as a fraction. Yeah, so always divide it out. Not terrible on that one, but it's still terrible. But I've had people write something like 325 miles over 4,258 hours. Looks good. Then you get one of those, maybe one of those, that kind of stuff. So always divide it out. Never leave an answer as a fraction. Divide it out. Take it to the right number, significant figures, and all that good stuff. Yeah. Any questions on that there? Yeah. Are you talking about math-wise with the deal? Yeah. So here's the deal with the ones, right? You really don't have to punch it into your calculator because if you multiply something by 1, nothing changes. or if you divide by 1, it really doesn't change. So you don't really have to punch it in. If you want to, you can. Nothing will really change. My recommendation maybe would not to punch it in because you might hit the wrong number, right, and then end up with something that's wrong. But technically speaking, what we're doing here is we're taking basically 32 times 1 times 1, and then we're going to hit equals, and that takes care of the top. And then we're basically going to divide by what's on the bottom, which technically would be 1. We would hit equals, divide by 32, and hit equals, and then divide by 4 and hit equals. Again, personally, I would probably shorten that down to just take 32. And since there's nothing really else on top, I would divide it by the 32 on the bottom, hit equals, and divide it one more time by what's on the bottom, which is 4, and hit equals. Again, just avoids perhaps maybe punching the wrong number when you're trying to hit 1 or something like that. So again, you don't really have to put the 1s in or anything like that, but if you do it correctly, it should give you the same answers. Yeah. Other questions? I was trying another one here, and an antibiotic doses, I'll spit that out, I think, of 500 milligrams is ordered. If the antibiotics is applied in a liquid in the form of 250 milligrams in 5 milliliters, how many milliliters should you give the person? We want to give 500 milligrams of this antibiotic. It comes basically as 250 milligrams and 5 milliliters. So this piece of information here is really another given piece of information, and they go together. So it's basically given as 250 milligrams in, basically, or per kind of 5 milliliters. That is essentially a conversion factor that's given to us in the problem, right? It's got 2 units. And really, it can be used like a conversion factor because it is like a fraction, right? So if we wanted to, we could also, if need be, which might be in this case, we could also flip this around and use it as like a conversion factor as well, again, because we have both of those units. Now, we are trying to find here milliliters. So I definitely know this is really more like a conversion factor that I could use because it's got milliliters and it also has the original units that I'm starting with, right? And as we were talking about earlier, right, sometimes people get to this point and go, I don't know which number to start with. Here I start with which number? The one that has probably the only unit by itself. So that's a good one to start with. So here we're going to start with the one that has the 1 unit because that is essentially the dose we want to give somebody, right? Is we want to give them 500 milligrams. We just want to figure out how much we should maybe stick them with a needle, I suppose, or in a beverage form, however you can do that. Again, we could think of it dimensional analysis way, so I'm just going to pop that up over 1, and now I could clearly see my milligrams are actually up on top. And I want to get rid of my milligrams, so I should use conversion factor on the left or right in this case. Should reduce the one on the right here, right? That has the milligrams in the opposite location. Remember as well that what we are looking for in the end, in terms of units, if it is just a single unit by itself, needs to end up on top, right, by itself. And that will put the milliliters up on top, which is what we're looking for. That will also, when we do our normal dimensional analysis math of multiplying and dividing, that will also take care of the milligrams to make them go away. And again, that leaves us just the milliliters up on top, which again is where we want it to be since that is what we're solving for. At this point, we just need to basically do the math part here. So once again, when we punch this in, I would go 500 times 5. I would hit equals. And once again here, really it's only the 250 on the bottom we need to divide by. So I would divide by the 250. And that's going to give me 10 milliliters in this case. First off, any question on the setup or that calculation? Now we do need to think about significant figures in our answer. So do I need to worry about the significant figures in this conversion factor? The answer is yes, I do, because this is one that's given to you in the problem. This medicine is not always in this form, right? It's not always 250 milligrams of 5 milliliters specific for this problem. So this is one where we do have to look at the significant figures. Top number here at 5. In this case, we actually have 2 real numbers here on both of them, right? So the 5 on top has how many significant figures? It does have 2. One on the bottom there, the 250 has That's both answers. Nobody said one, which is good, right? So it has two. Yeah, so it does have two. Here again, the zero at the end is not going to be significant because there's no decimal point written with it, right? So only the two and the five on that bottom number there is going to be significant. We also need to look at the first number, which has how many? R. If it's not one, it will be three in this case because this one actually does have a decimal point, right? Which does make those zeros at the end significant, right? So we do want to be careful when we're looking at these, right, to make sure, again, if there's a decimal or not a decimal. That means that's a lot of things to look at. But at the end here, how many significant figures should my answer have? Should have two, right? And does it have two the way I wrote it? It does not. So how can I fix that? Yeah, I could just put a decimal there, and now it has two. Can I put a decimal and a zero? No, because then it would have, right, right. The other way you could do it if you wanted to is you could do a little scientific notation throw back to first chapter, right? Do a little bit of that action right there, right? And again, those numbers before the times 10 part would be significant, and that would get you obviously your two significant figures as well. Yeah. Correct. So really, we put the one there, and in most cases, you usually will kind of not look at the one. Um, in this particular conversion factor, we actually did have actually two numbers that aren't one to look at. A lot of times, for example, if you take one from like that chart or something, one of the numbers will be one, and the other one will be the real number to look at. So usually one you wouldn't probably look at in most cases. Yeah. Is there a question? Yeah. Correct. So if you have a conversion factor that's considered and it comes from an exact sort of equality, you would not use it. So basically, most of the time, 90 some odd percent of the time, maybe even higher than that, maybe 98% of the time, the conversion factors you come across will probably be either like a metric to metric conversion. So if it's any type of metric to metric conversion, like centimeters to meters, grams to kilograms, straight up exact, you don't have to worry about it. If it's any type of like English to English sort of conversion, like 12 inches is a foot, something like that, straight up exact number, don't even worry about it. Yeah. The only time you really kind of two times places where you do have to kind of look at it is if you cross over from like metric to English type of thing, like the 946 milliliters is a quart, right? So that's one's US units, one's metric units. You do have to look at the significant figures in that type of conversion. The other time it happens is something like this, where the problem itself kind of gives you a conversion factor. Like in this case, it was how the dosis was. Maybe it could be a case like you're driving so many miles per hour or something like that. In those cases where the problem sort of gives you a conversion factor, because it's not like always like, 12 inches is always a foot, right? Medicine's not always in that sort of arrangement like that, right? So we would have to kind of look at it in this case. Yeah. Other questions? But I'll say this, and probably in most cases you could almost kind of ignore the conversion factors, but technically speaking, there are some that you should look at. And even in cases, and this is an odd case where actually it is a conversion factor that determines how the answer is. A lot of times the first number is either the right number of significant figures are pretty darn close to the right number of significant figures. Again, I won't say 100% of the time, but pretty high in the 90s% of the time. Like that first number, a lot of times is going to be probably be pretty close to their first number. Yeah.
Just like that.
Yeah.
So like, is it majority of the questions? Like, so we did the 500 first, and as a conversion factor array with it, do we take that first number always, even if there's more given number?
Uh, are you talking about to start the calculation?
Yeah.
Yeah, I would say in a kind of typical conversion type problem or something like that, a lot of times you will oftentimes have, perhaps if you have multiple sort of numbers given to you, a lot of times you'll usually have probably like one that's just like one number and one unit. And that's, I would say, in most cases, I won't say 100% of the time, but in most cases, that's probably a good starting point for you. You usually wouldn't want to start your kind of dimensional analysis in most cases with like something with two units, especially if you have another number that has just one unit. Yeah, so usually if you definitely have something with one unit, I would say probably in most cases That's going to be probably your starting point. The only time maybe you would start with something with 2 units is if you had something with 2 units and you're just converting those units like into other 2 units. Like if you want miles per hour, and you want to know how many feet per second that is, right? And it's just that number being converted into two of the different units. But most of the time, I would say you'd probably start with the one unit. All right, I want to try this one here. During surgery, a patient receives 5 pints of plasma. How many milliliters was given? Again, a quart is 2 pints, and a quart is 946 milliliters. All right, let's see how you're doing. So again, here, if we kind of pull out the information, we are given 5 pints, and we are looking for milliliters. So again, we want to kind of find a pathway to do that. Got a couple of equalities given to us. We got 1 quart, it's 946 milliliters, and we got 1 quart is 2 pints. So obviously in this case, we can go from pints to quarts and then take quarts over to milliliters as sort of our pathway to get there. Again, each of these equalities are going to give us two possible conversion factors. So again, we could have 1 quart is 946 milliliters. Our 946 milliliters is 1 quart. And for our other equality here, we can do 1 quart over 2 pints, are 2 pints over 1 quart. Good news here is we only got one number, so that's a good one to start with, I would think, in this case. And at this point, we got 5 pints. And once again, if it helps you, just throw it over one. And again, now you got kind of your fraction thing working out for you. And again, we want to go from pints to quarts. So we want to go opposites to cancel. Pints on top, that means on the left here, we will want pints on the bottom, so everything counts out correctly. That's going to give us 2 pints over 1 quart. Again, always multiplying the top, always dividing the bottom. That's where our pints will go away. Again, we could clearly see here now the quarts are up on top, so very easily to get rid of that, we're going to put quarts in the opposite location. And looking at our other options of conversion factors now, taking it for the second step here, we're going to go with the quarts on the bottom, which should be that guy right there. And that's going to get us here 946 milliliters on top, 1 quart on the bottom. Again, still multiplying the top and still dividing the bottom, so it doesn't matter. In there together. That again is going to cancel out our quarts. We again ended up with milliliters up that we're looking for, and again, that's where we want it to end up. 1 unit up on top is where you want it. So at this point, we're going to do the math here. So we're multiplying, and once again, you can multiply as many numbers as you want up on top. So you can take 5 times the 946. If you had a whole bunch of numbers, you could just keep multiplying them. The important part of the top part is once you're done multiplying the last number, make sure you hit equals. Yeah. And now we want to come back and divide by what's on the bottom. And here we only really have one number on the bottom to divide by. But if you had multiples, again, you would want to kind of divide by each one individually. That will always give you the right answer if you kind of put equals in between. Again, if you try to put too much in calculators, my experience is sometimes you end up with the wrong number, especially if you don't kind of separate it out correctly. So if we divide by 2 on the bottom there, we're going to give us 2365 milliliters in this case. First off, any question on this setup there? We now want to think about a little significant figure action. Do I need to worry about this conversion? I do, and it has how many significant figures? 3, right? This one, I don't need to worry, so that's all good. So this number over here, I also need to worry about, right? And that has 2. My answer should then have 2, which would take us here to the 3. And we would round up because the next number is a 6. And we would round up to 2400 milliliters. Not 24 milliliters. Why is 24 wrong? Yeah, different meaning, right? Although it has 2 sig figs, definitely just lost some meaning on that number there. We could also, as well, a little scientific notation, for old time's sake, 1, 2, 3 there. We could also do something like that if you would like to. Yeah. Any questions on that there? Take a look at another one here. All right, so next one, let's see, what are we doing? We are stranded 125 miles away from home. You got no money. You decide, heck, it's only 120 degrees outside. We'll take a walk. Seems like a nice day. If you walk an average of 55 feet per minute, how many days is it going to take you to get home? Yeah, so give it a go. See what you come up with here, let's guess. There's 5,280 feet in a mile. There are 60 minutes in an hour, right? By the way, how many hours in a day? 24, not 60, right? I get 24 hours on the day, one day. That happens a lot. Sometimes people go like 60 seconds in a minute, like 60 minutes in an hour, 60 hours in a day. Way too many hours. Okay, let's take a look, see how you're doing. So once again, if we pull out the information here from the problem, I got given to me, I am walking 125 miles. Um, we are also given sort of another value here, which is 55 feet per minute. So much like miles per hour or feet per minute, that again is basically like a fraction, right? So that is 55 feet per minute. And again, this is something that has kind of two units associated with it, which makes me think that perhaps I could use this as like a conversion factor, right? Since it's got two different units, which means technically I could flip it around if I needed to. A minute is 55 feet. Once again, as we talked about, number stays with the first unit, and it's basically one for the second unit there. So it's basically 1 minute on both of those, basically, is what that is. I am looking for how many days I'm going to be walking, right? So in this particular case, I have days, which is a unit of time. I have 125 miles, which is a length. And I have feet per minute, which is basically like a rate. And a rate, right, is how far in this case you're going in a certain period of time. So I am correct that perhaps I can use that as a conversion factor because that is what's going to allow me to go from distance, right, the 125 miles to time, which is days, right? Because that's the only thing that has like time in it, right? Is the minutes part of it. So I'm going to want to use both of those sort of values together, but there is one problem that I have, which is in the first number, right, it's in miles, and in the second number, the length or distance is in feet, right? So those are two different units. So we cannot just straight up use them together because they will not cancel out. So remember, for units to properly cancel out, they got to be the same unit on top and bottom, right? So they can't cancel if they're different. So I do have to do a conversion to get my really distance units or length units in the same unit. It is really up to you. You could actually do either way. You could take the miles and convert it to feet, or you could take the feet that's in that feet per minute and convert it to miles. It will come out the same. Probably the easier move is just to start with the thing with one unit, right? And that's where I'm going to start again with. So I'm going to take the miles and convert it to feet because when I do so, I should be all good to go to use this as a conversion factor because that also has feet in it. So again, we just want to get everybody into the same unit. So we could use this equality here to do that conversion. That equality will give us our two conversion factors here of 5,280 feet in 1 mile. Our 1 mile is 5,280 feet. So again, like I sort of mentioned earlier, probably most of the time, just go with that thing that has one unit. It's a good place to kind of start your calculation. I'm going to take my 125 miles. And once again, if it helps you, you can kind of just put it over one. And now again, we can see our miles are on top, so we want to get rid of it. So miles need to go on the bottom. So I am going to want to use my conversion factor here. And that's going to get me 5,280 feet on top and 1 mile on the bottom. I set it up with dimensional analysis, so I don't even have to think about the math, multiply on the top, dividing the bottom. Again, always that's the math, right? So it kind of locks the math part of it into place for you as well. You don't have to really think about it. 125 in this case times 5,280 feet. I'm actually going to get an answer in this case because I really want to use the answer in the proper units, which is 660,000 feet. I am going to get my steps in today, yes. And now that I have this in feet, it is good to go with our basically conversion factor, right? And we're going to use that conversion factor to go from basically distance now to time. So I'm going to take this 660,000 feet. I got all the right zeros. And again, I'm just going to kind of set it up like a fraction. And I want to get rid of feet, which means I should use my conversion factor up here, the one on the left or the one on the right? Yeah, the one on the right again, just keep it simple, right? It's got feet in the opposite location. So that's going to give me 55 feet per minute. Again, I'm still dimensional analysis here, so I'm multiplying and dividing, and that is going to get rid of the feet. And if I stop the calculation right at this point, I'm in units of minutes, right? And that's good because ultimately I want to get to days, which is also time, right? So now I got it into the units of time, which is what I'm really looking for. Again, basically using the conversion factor that was given to us in the problem to do that, right? And we could do that because, again, that conversion factor had basically distance and time, and which is a rate associated with it. At this point, we now just need to take basically our minutes to days, right? So we could use our other equality here to do that. So minutes are on top, so I definitely know minutes should go on the bottom, right? So there are 60 minutes, right, in 1 hour. And that is basically from this equality, which obviously would give us our two options, 60 minutes, 1 hour. Our 1 hour is 60 minutes. And again, I don't have to think about the math because on top gets multiplied, on the bottom gets divided. Once again, when we divide that, now my minutes go away. And I'm at units of hours now, right? So I'm close to where I want. Now I need to take it from hours to days, right? So again, 24 hours in a day. I have it set up so I could clearly see hours are up on top. So I do need to put hours on the bottom here. And that means that 24 hours should go on the bottom and 1 day should go up on top. Math wise, still multiplying the top and still dividing the bottom here, right? Hours will now cancel and I am now left with days up on top, which again is what I'm looking for, right? And it's up on top by itself, which is where it wants to be or should be. First off, any question on that setup there? So hopefully you can kind of see keeping things very nice, organized, top and bottom fraction is just the way to go. It takes out a lot of the thinking, the rearranging. Just got to remember those three things. Opposites cancel, multiply the top, divide the bottom. So let's do the math part of it here, which is there's really not much to multiply on the top. Everybody here is basically a 1. Again, this is basically a 1, even though it's not written, but it's basically a 1. So we can basically take 660,000. I'm going to divide by what's on the bottom. Once again here, I am not going to throw all these numbers into my calculator at once because I might want the right answer, yes. And I've seen a lot of people do that and not get the right answer, but some have got the right answer. So here I'm going to take my 660,000. I'm going to divide by the first number, which is 55. So I'm going to divide by 55. I'm going to hit equals. I'm going to divide by the next number, which is 60. I'm going to hit equals. And I'm going to divide by the last number, which is 24, and I'm going to hit equals. And I'm going to have a lot of 3's on my calculator and an 8 in front of it, right? And a bunch of 3's. A bunch of them. Go days here, yeah. All right. So now that we got our answer, we then need to think about kind of significant figures and what it should be. And again, since we set it up with dimensional analysis, it is going to be sig figs. 1 day is 24 hours. That looks like an exact thing. I don't have to worry about that, I hope. It's also 60 minutes in an hour. That also should be an exact thing. How about the 55 feet per minute? Do I need to worry about that? I do, right? Because again, that's sort of specific to the problem. And the only number I really need to look at here is the 55, which the way it's written has how many significant figures? It does have 3. How about the first number? Do I need to worry about that? How many significant figures does the first number have? It actually does have 3 because remember, this number here is not really the first number. This number really came from this number, which technically has 3 significant figures, which if I wrote it correctly here, should technically have 3 significant figures, but I didn't because I wanted to use the whole number, not round too much. So really this number here should have actually been 3 significant figures, probably written in scientific notation if I wanted to do it correctly. That means really my answer here should end up with, everybody's got 3 basically significant figures. So 8.33 days. So a reminder that although I did use 660,000, that number did originate from here, which meant my 660,000 really should have 3 significant figures. And along with the 3 for the 55.5 would give me obviously 3 significant figures on my answer. Any questions on that there? It's a lot of walking. So